So in today's lecture, we're going to talk about how to fit a logistic regression model in R, and also how to interpret the coefficients and other outcomes. For illustration purpose, we're going to use this heart disease data. It has about 462 observations, and the response variable is CHD. It's 1 means the disease is present, and 0 means absence. And there are 9 covariates. Most are numerical features except family history, which is a binary covariate variable. So the grammar is almost the same as a linear and model LM. You just use GLM. And we're also going to tell R and the family is binomial because GLM is really a big umbrella, contains a lot of other models like Poisson regression. Here we just focus on logistic regression. And once we get our GLM fit, we run a summary. And first we're going to see this coefficient matrix. The first column are the estimated. The first column is estimated coefficients. We have intercept and the coefficient associated with each of the features. The interpretation is the same as GL and regular LM. For example, for SBP, we will say, well, if we increase SBP by 1 unit, we're going to increase the response by 0.0065. But what's the response in the logistic regression model is log of the log of p over 1 minus p. And sometimes they call it log odds because odds basically is p over 1 minus p. And so the interpretation is as follows. If we increase our unit x1 by variable x1 by 1 unit, and then you can just work out this calculation, you're going to find out we basically increase the log odds by beta 1. So the interpretation of this coefficient beta 1 would be, if we increase x1 by 1 unit, then we'll change the odds by exponential of beta 1. So if beta 1 is positive and exponential beta 1 is bigger than 1, so that means we're really increasing the odds. But if beta 1 is negative, then exponential beta 1 will be less than 1, so it's like less than 100%. Then we're basically decreasing the odds. Let's go back to look at this and look at the outcome for the heart disease data. For most of the features, the coefficients are positive. So if we increase them by 1 unit, that will increase the corresponding odds. And what's interesting is the coefficient for obesity is actually negative. That means if we fix all the other features and only increase obesity, someone has more body fat, actually going to have a lower chance of having this heart disease, which is very counterintuitive. But now I think all of you should know how to interpret it or resolve this contradiction. It's all because of the collinearity among the features. You can look at the correlation of obesity with all the other features. You can find out most of obesity is almost positively correlated with everybody else. So because all the other covariates get positive coefficients, so they already sort of imply a positive contribution from obesity, and that implied positive coefficients might be bigger than what the positive contribution obesity should contribute. So to offset that, we get a negative coefficient for obesity. And as I mentioned before, in logistic regression, inside the logistic regression, at every iteration, we're basically fitting a weighted least square model. So imagine at the last iteration, we're fitting a weighted least square, and we know all the weights. So we can just extract all the outcomes as what we usually have from a linear regression model. For example, we can get the covariance matrix for the coefficients. And further, we can extract the diagonal term, take a square root, and that will be the standard error for each feature. And then the estimated coefficient divided by standard error will be z value. Here we don't have t value because the resulting, that ratio is no longer follow a t-distribution, but we're going to use an approximation theory, and the estimated coefficient divided by standard error will approximately follow a normal distribution. So that's a z-value. And then using the normal distribution, we can calculate the two-sided tail probability, and that's our p-value. So we're going to look at the smaller the p-value, and the more significant that coefficient is. We don't have residual sum of square or sigma estimate. Instead, we have null deviance and residual deviance. So what's deviance? And the deviance is defined to be 2 times log likelihood of the saturated model minus log likelihood of the current model. And so what is log likelihood? For every observation xi, yi, we have the estimated probability pi hat. If yi is equal to 1, what's entering the log likelihood computation is log of pi. If yi is equal to 0, and what's entering the calculation is log 1 minus pi. So we know how to calculate log likelihood. Now, what is the pi in the saturated model? In the saturated model, we assume that at every location xi or every feature xi, we observe multiple binary outcomes. So in this case, there are ni outcomes for y. So in the saturated model, we would estimate the probability at each xi independent of all the other locations. So pi will be just the average of those yi's we observed at xi. What is a null model and the log likelihood for the null model? Well, in the null model just refer to the case where we're not going to use any features. We only use the intercept. So our prediction at every xi should be the same, which is p0, which basically just observe the frequency of y. And what is the log likelihood of the current model? Then we just replace our pi just by the current model, the estimate of pi from the current model. Now, if all the xi's are unique, that means our ni is equal to 1. So at every location xi, you either observe y equal to 1 or 0. So you estimate the probability is either 1 or 0. And you're going to find out the corresponding log likelihood. Every term is just log 1. So the log likelihood for the saturated model when xi's are all unique is basically 0. So if all the xi's are unique, you're going to find out the deviance is basically minus 2 times log likelihood of the current model. And so that's the case for our hard data, because all the xi's are unique. So you can calculate all the deviance just minus 2 times log likelihood from the null model for the null deviance, and minus 2 log likelihood of the fitted probability for the current model, and that's the residual deviance. So here I did the calculation, and here. Now once we fit a model and we'll encounter a situation as what we encountered before with linear model. There could be a lot of features and only a subset of them will be relevant. So we're going to do our variable selection. And we can use AIC and BIC because for logistic regression model, we have a likelihood. And in terms of the algorithm, for AIC and BIC for logistic regression model, and it's impossible to go through all of the models, and we cannot use this log subset command because we're not dealing with L2 loss. So we have to use those Grady algorithm either stepwise, backward, or forward. Here I'll show you how to do that in R with a stepwise. First we do stepwise with AIC. So we just call step and provide the model fitting from the full model. And we're telling R, the biggest model we're going to explore will be the model with all the covariates from this data frame. And the smallest model we're going to explore is the intercept only model. So an R will start with the full model and then try different actions. Basically just remove each of the existing covariates or don't do anything. And then we're going to calculate the corresponding AIC and rank the AIC from small to large and take the action corresponding to the smallest AIC. In this case, we're going to remove alcohol. And then we get to second stage. Again, we're going to try to remove each of the existing covariates or don't do anything or add back the alcohol. And we rank those actions by AIC value, and the smallest AIC would lead us to continue removing a feature. And then we keep doing this until at a certain point, and don't do anything, actually going to have the smallest AIC, and then we're just going to stop. And we can just grab the existing model. And I think we end up picking 5 covariates out of 9. And you can do BIC, and the command is almost the same. Here we're just telling R, no need to show us the intermediate results. And for BIC, we have to set K to be log n instead of the default value 2. And so it turns out BIC and end up picking the same model as AIC, a model with 5 covariates. And we can also use lasso or rage or combination of them. The algorithm almost the same as the linear model because, as I mentioned before, inside logistic regression we are basically just doing a weighted least square. So we're going to have so we can easily extend the existing algorithm for linear model with lasso to logistic regression with lasso penalty. So the log likelihood we want to, the objective function we want to minimize is going to be minus log likelihood now plus L1 penalty over the coefficient vector beta. So we're going to do, let's close this. So in order to use lasso, we call GLMnet. We provide the data matrix, the response vector y, and family is binomial. Alpha is equal to 1, meaning only lasso, no rage. And you can plot the estimated the path plot. And you can also do cross-validation. Now we know how to interpret those 2 dashed lines. This is lambda mean, so that's a lambda value, gave us the smallest cross-validation error. And then we will regard any error below the upper, 1 standard error. So this is the 1 standard error above the smallest error, but then any error below this would be regarded as equivalent. Then we're going to go back to find out the largest lambda and whose corresponding arrow is within this arrow bar, because we want to pick the model with the largest regularization but still have similar and prediction and accuracy. So this is basically lambda 1 SE. So if you really care about prediction error, use a model determined by lambda mean. But for variable selection, let's look at 1 and SE. So you're going to find, here's how you extract the coefficients. You're going to find out some of the coefficients are going to be exactly 0. And similar to AIC, BIC, lasso also end up picking a model with 5 features.